Okay. Let's begin. The first question is, what is reality? We don't know. How do we say something is real? We say so by our five senses, right? And these five senses are: first, vision, that is, we grasp the reality through our eyes. Then, audition or hearing, okay? We have our ears, and through which we perceive the sound. Third is olfaction. Olfaction, we get smell from our nose, okay. Fourth is touch. We have the skin on which we have various types of corpuscles, and through which nerve impulse comes and goes, and this way we get the sensation of touch sensation, right? And the fifth one is that we get taste, or we can call it gustatory or gustation, whatever you want to say. We have a tongue. On this tongue we have various parts which perceives various types of tastes, and everything we see around us, we hear around us, we take smell of. These data are processed in the wonderful structure which is called brain, and through which we perceive reality. So everything we see as real are nothing but these five senses and the data which we collect from it. So let's start with vision. So what is vision? So the first thing is, when light rays come, suppose this is an object O, and here some part of the light is absorbed, some part of it is refracted, and some part of is reflected. And this reflected light which we see from our eyes gives us the sensation of vision. Okay, so this is vision. So to see, what do we require is light. And let's talk about light. This was one of the most controversial topics throughout the history. We had two theories. First were theorists who called as light as particle, and the most famous proponent was Newton, and the second one was Huygens, and he called light as wave. So let's talk about them one by one. Newton said that light travels in straight line. It follows the principle of reflection, refraction and all, and hence light is nothing but a particle. Okay, so he imagined light to be stream of particles. Okay, and what did Huygens think? Huygens thought that light is nothing but it's a wave. So he gave the wavefront theory. What is wavefront theory? It's nothing. Let's say this is a point of light which we consider as light object, light source. Okay, so from this source he imagined corpuscles of light. Okay, and these were called as wavefronts. And let's say this is one wavefront. It can be represented by various types of diagrams, and which we will do one by one. So let's say here is a light, and from here light is passing. Okay, so let's zoom it in. So let's say here is one, here is one, here is one, here is one. This way there are various types of wavefronts. Let's say we have five wavefronts here. So we will have multiplication of these wavefronts in the propagation of light. So he gave wave front theory. Now till the end of 19th century, it was not clear what is light. With the evolution of Maxwell's equation of electromagnetism, we found that light wave is nothing but one of the parts of the spectrums of electromagnetic wave. It is just like ultraviolet rays, it is just like the radio waves, it is just like the microwaves. Light wave is nothing but a part of the spectrum of electromagnetic wave but falls between the range of 300 nanometer to 700 nanometer, and this was called as visible range. So this is the only visible part which we can perceive through our eyes, and this is what we call as light. And according to the wavelength, according to the frequency, we have the whole series of electromagnetic waves. So now what which we got as light to be nothing but an electromagnetic wave with a fixed velocity of around 3 into 10 to the power 8 meter per second. Okay. Now, debate was still going on. People were not clear how light should be perceived. But once Maxwell's equations were given, it was generally perceived that lights are waves until and unless with the discovery of photoelectric effect. Photoelectric effect, and which was elaborated further by the great Einstein, he proposed light is behaving like a particle, and he called this particle as photon. And this, boys and girls, laid the foundation of light behaving as a particle. Before that, we had de Broglie's hypothesis, which we can derive now. So, according to the equation of E is equal to mc square of Einstein, and secondly, the quantum mechanical energy given by Max Planck, E is equal to h nu or E is equal to hc by lambda. If we equate 1 and 2, we get E is equal to mc square, E is equal to hc by lambda. So this C and C gets cancelled out. We get the wavelength is equal to h by mc or h by p, where p is momentum. So this was hypothesized by de Broglie, and from here we got this special equation. And this established light to be of dual nature. Isn't it fascinating? Light is both particle and wave. And the fundamental unit of light was called as photon. Later on it was observed that not only light and not only photon, we have variety of subatomic particles which also act like wave. For example, we have electron. Earlier we thought electron was a particle, as emphasized by various previous scientists. We have the Thomson's model, J.J. Thomson, who said that electron is just like the pudding in a plum. We had the plum pudding model. Thereafter, we had various types of experiments and theories which further emphasize the fact that electron is a particle. But until and unless we came across a very special experiment, and this experiment was called as double slit experiment. This double slit experiment is famously called as Young's experiment. What did it say? Let's suppose here is a light source and we have a slit over here. This is a slit. If light was a particle, it should travel in straight line. And let's say here is a screen. If light was a particle, we should be getting the maximum amount of density in the middle. And if we observe from here, we will see the most amount of intensity at the center, like this. Okay. If we observe from here, this is the screen. If we observe, we will get the most amount of intensity at the center. Again, light acts as a particle, it moves in a straight line, and here is the slit. So we will get the maximum amount of intensity at the center if it was a particle. Now let's do this experiment with two slits. Here was only one slit. Let's do it with two slits. Here one slit and here is another. And this is the light source. So from here light must be going like this way. If it was a particle, in the screen we should get something like this, isn't it? If it was a particle, we would get maximum intensity at these two peaks. Okay, but when we did this experiment in an isolated environment without any observer, when there is no observer and we do this experiment in an isolated environment, what we got is light acts like a wave. So let's say this is a light, and let's say it travels like a particle. So like this it will propagate, and from here again as a wave. So if it act as a wave, it will have interference pattern, and this was the greatest achievement of this double slit experiment, where instead of having two peaks, what we got was interference pattern of dark and light. So here is the peak, but two troughs of the waves have collided. So this gives us the dark part, and when the two crusts have collided, we get the light part. So we get the fringe-like pattern of dark and white, and this, ladies and gentlemen, give the idea that light acts as a wave, not as a particle. But just now we saw that when there was an observer, when we saw the whole experiment, it acted like a particle. But when there is no observer and the experiment is performed in an isolated environment, it acts like a wave. And this was the founding stone of quantum mechanics. Or let's say this experiment gave the whole notion that the physical reality or the reality of the entire universe might not be as simple as Newtonian physics. It is something very deep and very counterintuitive. And this gave the idea of quantum mechanics. Did you find this fascinating? It is very fascinating. We'll talk about various ideas of quantum mechanics in the later videos. So, what did we see for now? We saw that light acts as particle as well as wave. When it acts as a particle, when there is an observer. But when it is performed in an isolated environment and when there is no observer, it acts like a wave. Not just light, also electron. Electron also acts like a particle but as a wave. And this laid the foundation of quantum physics. We cannot say where an electron is. Let's say this is a wave. Here are the maximum chances of finding an electron when we are not observing. But as we observe, we find electrons here or here or here. It can be found anywhere. But these are the probability distribution. What are these? We will see in later classes. For now, thank you.